Section 10.5, Part 1, Area and Arc Length in Polar Coordinates. Let's begin by looking at how to find the area of a polar region. So this is area that's basically enclosed by a polar curve or even curves. Okay, so to begin, here's kind of the picture, right? We have some polar curve in space, and we want to find a region, right? And we're going to kind of know where that starts and ends based on different angles. Okay, that's kind of where we start, our starting theta, kind of our ending theta, because obviously polar curves have inputs of theta. So in order to calculate this, what we're going to do is take this region and basically break it up into sectors. Okay, so if we slice this up in a little bit of pieces, every one of those little pieces can be viewed as a sector. Now remember, the area of a sector is what we're going to be focusing on here. So when we talk about each one of these, obviously they're going to have a central angle. That's going to be the amount of theta we're working with. And then clearly the radius, right, that's just going to be that R value for the function. So as it changes throughout the region. Now, as a reminder, to find the area of a sector, it's essentially part of a circle, right? So when we want to talk about how much of the circle we want, we're basically talking about the central angle part, right? The theta over 2 pi, that amount of the circle times the whole area. Okay, so this fractional amount times the whole area gives us the area of a sector. So if we simplify this expression, clearly the pi's are going to cancel out, and we can view this instead as just 1/2 r squared, delta theta. So this can give us a quick idea on the area of each of these little individual sectors. And of course, like all of calculus, once we can geometrically describe all these individual little things by using integration, we can add them and sum them all together to create the entire area. So when we talk about the area enclosed from theta equals alpha to beta, this is what it's going to look like. There's a 1/2, and I'm going to go ahead and just put that out front, and that's just, of course, r squared, which, I guess, is a function of theta squared, and then the d theta, of course, is that incremental change in theta. So it's a very easy formula to use, but one of the things we have to realize and work with is knowing where we start and end, okay? Because there's a lot of different kinds of polar graphs, and to be honest, finding alpha and beta, that's going to be one of the bigger things we have to take care of. Oftentimes we want to solve for 0. Oftentimes we're definitely going to be using a lot of symmetry, so we want to make this as easy as possible and also be able to use some easy angles. So for our first example, let's look at the rose curve here given by r equals 3 cosine 3 theta. Now what we want to do is find the area of one petal. So our goal, and I'm just going to highlight this right here, is to find the area of this region. Now that's fine. However, it might be more, I should say easier for us if instead of finding the area of an entire petal, maybe we just find half of it, and here's why. One of the things you want to do with a lot of these problems right away is figure out where the zeros are. You want to figure out when theta puts you at the pole, okay? So the first thing I'm going to do is I'm going to say, when are we at 0? So let's take our 3 cosine 3 theta and solve the equation, figure out when we're at 0. Well, clearly that means it's going to happen when 3 theta is going to be equal to, pi over 2 or 3 pi over 2 or even 5 pi over 2. And again, I know there's 3 zeros because remember with a cosine, we're going to start out here at the edge of the petal and then pass once, twice, 3 times through the pole to make that happen. So I know there's 3 of them. And solving for theta tells me that those zeros happen at pi over 6, at pi over 2, and at 5 pi over 6. Now again, I'm only interested in finding the area of one of these petals. Now, if I plug 0 in for theta, I know I start again right here. And so if I know the next time I hit 0 is going to be at pi over 6, that means what we can focus on is that when we look at increasing values of theta, the graph begins here, and by the time I hit pi over 6, I'm here. So if I consider maybe doing an integral from 0 to pi over 6, that's actually going to give me, if you will, the top half of this petal. And because the numbers 0 and pi over 6 are really easy numbers to work with, then what we can do is we can double it. Okay, so in this case, my strategy to find the area here is I'm basically going to integrate from 0 only to pi over 6. And again, I know that draws out only the top half of this, but because it only draws out the top half of it, then what I can do is I can just double that idea, okay? So that's going to be the strategy. We're going to double the integral of all of this, okay? Now remember, when we calculate the formula, there's still a 1/2 involved. We're going to square r and all that. But the idea is, where do I start and end? And if I can use symmetry to make it easier, that's a really good decision, okay? So by going from 0 all the way to pi over 6. We generate the top half of my petal. If I simply make that calculation and double it, we get the whole thing. So let's go ahead and set this up. So the area is going to be twice the formula. And remember, the formula is 1/2 the integral of our limits of integration. We're going to go from 0 to pi over 6. And then, of course, our r, which is 3 cosine 3 theta. We're going to square that whole thing, d theta. Okay, and again, this is the easiest way to do it. Easy numbers to plug in, and oftentimes if we can double it, it makes things a lot easier. So if we go ahead and get ourselves ready to anti-differentiate, let's square and simplify the front. Now, the 2 and the 1/2 clearly make 1. And if I go ahead and square the inside part, this is just going to be 9 cosine squared 3 theta. So we have to think of ourselves, how do we want to go ahead and anti-differentiate that? Well, as always, if we have a cosine squared, we can just rewrite that with power reduction. So that means I'm going to be working with my integral from 0 to pi over 6. And I'm going to replace my cosine squared with 1/2 plus 1/2 cosine. And don't forget, you double the angle, so this becomes 6 theta. Now, there was a 9. I'm just going to throw that constant out front. And don't forget our d theta. All right, so now we can actually find our antiderivative. So the antiderivative of 1/2, of course, is simply 1/2 theta. And then by a basic substitution, this is going to be 1/12 sine 6 theta. Okay, and of course, we're going to be evaluating this from 0 to pi over 6. So let's go ahead and plug that in. If I plug in pi over 6, that's going to give me obviously pi over 6 divided by 2, which is pi over 12. In my first quantity here. Now, if I plug pi over 6 into the other one, that's going to give me sine of pi, and that's just 0. So this is plus 0. And then, of course, plugging 0 into both of those gives me 0. So this actually works out pretty nice. So this is basically 9 pi over 12, or if I simplify it, 3 pi over 4. Let's try another example, but this time calculate the entire area enclosed by this cardioid, right? It's a limacon, but obviously with that touching the pole with that sharp little corner here, this is technically a cardioid, especially because A equals B. Now, in this case, again, we want to find our zeros. I think that's a great place to go. Solving this, of course, for 0 would really ask me where theta, right, is going to make cosine equal to, -1. Because if I subtract 2 and divide by 2, it's just going to be -1. And cosine is equal to -1 at pi. So that means that, again, when we start, and by the way, we're starting here at 2. I know that because plugging in 4, I should say. When you plug in 0 for theta, that just becomes a 1. 2 plus 2 gives me a 4 for my starting point. So beginning at 0, I'm here. And then as I integrate all the way to pi, it takes me right there to the pole. And it's pretty obvious this is a graph that would go from 0 to pi to get there, but just to double check, those are the numbers I want. And again, I want to take advantage of symmetry. So even though, again, I'm looking for the area enclosed entirely by the cardioid, what I'm going to do is I'm just going to integrate from 0 to pi and then double it. Okay, and again, that's something you're going to notice a lot with the integrals in polar. Lots of these graphs, at least the ones that we work with, oftentimes have symmetry. And if we can take advantage of that and have easier integrals to evaluate, I think it's a great idea. So obviously here, we're going to go ahead and take care of it this way. So that means, just like our last problem, to find our area, we're going to double our formula. And again, the formula is 1/2 times our integral. And again, this one we're starting at 0 and going all the way to pi. Our r is going to be 2 plus 2 cosine theta squared d theta. Okay, so let's do the same thing we did before, clean things up. Clearly, the 2 and the 1/2 again cancel out very nicely. We do have to square this entire thing, so that gives us 4 plus 8 cosine theta plus 4 cosine theta squared. Okay, remember we got to FOIL that thing out, d theta. All right, so our next piece obviously is doing whatever we can to make this look as nice as possible. So I guess the first thing I'm going to do is I'm going to look at the 4 and the 8 and the 4 and at least take out whatever I can. So in this case, I'm just going to take out a 4 just to make it a little easier on my simplification. Okay, so I'm going to take out a 4, and that, of course, in my integral is going to leave me with 1 plus 2 cosine theta. And remember, I'm going to replace my cosine squared theta with 1/2 plus 1/2 cosine 2 theta. Again, we want to use that formula again since we have the higher power and reduce it, if you will. And then I think, combine like terms a little bit. So I'm going to take my 1/2 and my 1 and put that together to be a 3/2. And then, of course, I'll have a 2 cosine theta. And then I'm still going to have that 1/2 cosine 2 theta. All right, so let's find the antiderivative. Now, again, on the outside, I'm going to have a 4. Now, the antiderivative of 3/2, obviously, is going to be 3/2 theta. And then it'll be plus 2 sine theta. And then, again, with this one's a basic substitution. We will end up dividing by 2 in the substitution. So we'll get a 1/4 sine 2 theta and evaluate that from 0 to pi. So evaluating this, we're going to have 4 times, plugging in pi gives me a 3 pi over 2. And then, of course, the sine of pi is 0. Sine of 2 pi is 0, so we got that. And then minus, well, plugging 0 into all those just gives 0 for every single one, so that's nice and easy. So the whole thing here is going to work out just to be 6 pi. Now, the next thing we want to talk about, because now we've done area, is talk about length, right? So this formula should look relatively familiar. This is now the polar version of arc length. So this calculates the distance around the curve from angle alpha to angle beta. And again, looking at the form of it with the radical, the things being squared, it really is coming from that same parametric idea that we used before. So let's try a quick example. We're going to calculate the length of this cardioid. Okay, this is 1 plus sine theta, and again you can see the picture right here. And what we want though is only the length of it that is above the x-axis. Okay, so first off, it's not the entire cardioid, so we want to know, when it's going to need to have that happen. Well, clearly looking at the picture, we want to start at 0 because 0 is going to put me right here, and then we want to integrate all the way to at least pi, right? Or because there's a sine, I want to take advantage of symmetry. What if I only integrated up to here, okay? So what I'm going to do actually is, instead of going from 0 to pi, which is fine, I suppose you could do it, instead of going from 0 to pi, which is the length I'm looking for, I'm going to go from 0 to pi over 2. Now, I think the reason I really want to do this is going to come out in the algebra here in a moment when I simplify and do some trig. But I will admit you could go from 0 to pi and get the right answer, but I feel like it's going to be easier, and you'll see what I mean in a moment, if I simply find the length from 0 to pi over 2 and double it, okay? So let's go ahead and set this up. All right, so the first thing I need to figure out, obviously, is what is r prime, because obviously I need to figure out that part of it as we plug in the formula. So in this case, r prime is just going to be cosine theta. So what I need to do for my formula is take r squared plus r prime squared, okay? And just like I did when I first did arc length, I like to simplify this first before I put it in the radical. So r squared is going to be 1 plus sine theta squared, and then of course the other part, r theta squared, so r prime squared is going to be cosine squared theta. Now, if I go ahead and simplify this, remember 1 plus sine squared, right? And then if I add a cosine squared, if you work that out and simplify it, you can make this into 2 plus 2 sine theta. Okay, so I'm going to skip a little bit of steps. But really, when you think about it, this is just going to be 1, this will be 2 sine theta, and then a sine squared. But obviously, the sine squared and cosine squared make a 1 that you combine with this to become a 2. So just some quick simplification can give you this expression right here. So let's go ahead and set this up. So again, we use lowercase s for arc length, and we have a 2 on the outside because, again, I'm going to double my region. Okay, normally it wouldn't be there, but since I want to double 0 to pi over 2, just make it a little easier on myself, we're going to put a 2 out front. Okay, so we go from 0 to pi over 2, and of course we're going to have 2 plus 2 sine theta. Now, because it's under the radical, we're going to have to get a little clever about how we do this. Now, the first thing I'm going to do is I'm going to try to get that 2 out of there. So on the inside of this radical, I'm going to factor out a 2. So underneath the radical, I'm going to look at it like it's 2 times 1 plus sine theta. And then because it's a product, I can push out a square root of 2. I'm doing that to make my numbers as nice and simple on the inside as I can. Okay, so I have a 2 on the outside, and like I said, I'm going to break up my radical into basically the square root of 2 times the square root of 1 plus sine theta, if you will, which means I can put that constant out front. Now, the reason this is really helpful is under my radical now, I just have a 1 plus sine theta. This is going to be a lot easier to work with algebraically. So what I got to do is figure out a way to deal with this. Okay, now what I'm going to do actually is I'm going to go in here and I'm actually going to multiply by a conjugate, right? It's going to still be another radical, but it's going to be a conjugate feel to it. So I'm going to use that 1 minus sine theta. And I'm doing that because I'm looking for squaring and Pythagorean ideas to help me simplify this thing, okay? So I'm going to go and again take my conjugate and write that over itself, and I'm going to keep under radical so I can put it together. So what this whole thing becomes on the outside is, again, I still have my 2 radical 2. But when you think about simplifying the inside, in the top, if you multiply 1 plus sine squared, so 1 plus sine theta times 1 minus sine theta, those two are going to create a difference of squares, which is going to be 1 minus sine squared. And obviously 1 minus sine squared is equal to cosine squared. And if you take the square root of that, that's just going to be that. Now I'm going to leave it just for a second so you can see it, but that's kind of why I did that. So this right here is going to give me something to make that radical go away. Now I still have this left in the bottom. However, because I'm going to be able to get rid of the radical on the top, I'm going to be able to do some substitution. So I can go ahead and take the square root of this to make it just cosine, okay? And I'm going to come back to that step in a minute and talk about something, but for right now, I just want you to see why I'm doing what I'm doing. Okay, so on the top, I have a cosine theta. On the bottom, I get this 1 minus sine theta d theta. So that means clearly at this point in time, I can say, we'll let the radicand on the bottom there equal our u. So our du, right, is going to equal the derivative here. We'll put a negative in front because I need to get a cosine theta d theta, and I can make my substitution. So when I make my substitution, I'm going to get a negative in front. My limits of integration are going to change, and obviously if I plug in my thetas here into this expression to get u's, what that's going to do is make me integrate from 1 to 0, which works because obviously the negative in front and this negative here is going to get taken care of. So I'm just left with a u raised to the negative 1/2 du. Very easy antiderivative. So we'll have a 2 radical 2 here, because I'm going to go ahead and flip my limits of integration. So I'm just going to change that sign. This will be 2u raised to the 1/2, and since I changed the sign, we'll go from 0 to 1. All right, so plugging it in, we got 2 radical 2. Plugging in a 1 just gives us a 2. Plugging in 0 gives us 0. So this becomes 4 radical 2. And that is, of course, the length on this cardioid from here to here, all the length above the x-axis. Now, what I want to point out, right, and this kind of goes back to the step over here, is that when you look at the square root of cosine squared theta, technically it equals the absolute value of cosine. And that's just a whole situation that when you square root something being squared and you get that odd power, you know, it could have been positive or negative, right? It's because you're squaring it and then square rooting it. So technically, it should be equal to the absolute value. The reason I didn't put that over here is because looking at my limits of integration, right, from 0 to pi over 2, that is where cosine is positive. So on this limits of integration from 0 to pi over 2, it's okay for me to replace this with just cosine theta, because that is the same thing as absolute value. It is where it's positive. I bring this up because if you decided in the original problem that instead of doubling it and using symmetry, you just said, you know what, let's just integrate from 0 to pi. And that's fine. However, once you get to the work, right, and you get to the step that looks just like this, then what's going to happen is you're going to have to break that up a little bit. Okay, so obviously you would have taken this radical 2 out, but technically you would still have this cosine theta on top. And I say that because when you choose to integrate from 0 all the way to pi, that means that you have part of it. Okay, so like this part here where cosine's positive, but this part here where cosine's negative. So what happens is you got to take this, again, the integral just of the whole thing, and you got to break it up into 2 pieces, right? You got to do one piece from 0 to pi over 2 where you have a cosine in the top, and then you have to add another integral where it just goes from pi over 2 to pi where you use a negative cosine in the top. And again, that makes sense because the angles you're using over here produce negative cosine values, but again, it technically has to be positive, so that's why you have that sign change. That's one of the reasons I really like to take advantage of symmetry and, especially in this problem, remain in the first quadrant. Okay, so just something to think about as you're doing a problem like this.